So hello again everyone, welcome back from your break. Now we will continue with types of electromagnetic radiation. And those types I'm referring to are X-rays and gamma rays. X-rays, which is an electromagnetic radiation type, has energy greater than 10 electron volts and is therefore classified as an ionizing radiation. X-rays can go up to 100 kiloelectron volts, whereas gamma radiation, the photon energy goes above 100 kiloelectron volts. X-rays and gamma rays are weightless packets of energy and they are called photons. Gamma rays, in comparison to X-rays, are a lot stronger and can pass completely through the human body. And as they pass through, they have the potential to cause biological damage to the DNA. Because humans are unable to control natural background radiation, exposure from artificial sources that can be controlled must be limited to protect the general population from any further biological damage. As you already know, the energy of a photon is directly proportional to its frequency. So once again, the higher the energy, the higher the frequency. We know that X-rays originate in the electron cloud around the nucleus. We know that X-rays travel at the speed of light. It has no mass and it has no charge, so it does have a high frequency and it has a short wavelength, which represents its power. It can be dangerous if not used properly. So we know as medical radiation technologists or medical radiographers, we can choose the energy by setting the kilovolt on the X-ray machine. We know that the only thing that distinguishes X-ray from gamma ray is that the X-rays can produce interactions that occur when the electrons are striking the anode or the target of the X-ray machine. And then they convert this kinetic energy into X-ray photons and to heat. I'm sure you've learned in other courses that 99% of the energy is in the form of heat and only 1% comes out in the form of an X-ray. So X-rays are considered a low linear energy transfer type of radiation. While X-rays are linked to a slight increased risk of cancer, however, there is an extremely low risk of short-term side effects. High radiation levels can have a range of effects on the skin and on the patient, such as skin burns and hair loss. If you see the image here in front of you, this is of a patient who had repeated CT scans to one area of his head, and he suffered some hair loss because of high radiation doses received during that time period. X-rays is quite penetrating. If you look at the image on the right, it can only be stopped by a thick sheet of lead or a well-constructed room that is made of concrete slabs or bricks, or perhaps concrete and a water combination to stop the X-rays from penetrating right through. So when the electron strikes the anode, we know that the kinetic energy is going to be converted into X-ray energy. The most common electron anode interaction is the Bremsstrahlung interaction, or the Brems radiation. So here you can see the electron stream hitting the target, and the X-rays are being produced. And looking at the atom itself, you will see that the incident electron comes in, it slows down near the nucleus, because the nucleus has a strong binding energy, and then it changes direction as energy is lost. It becomes an X-ray. So now we'll have a look at gamma rays. Gamma rays is represented by the symbol above. It is also a form of electromagnetic radiation. It has no mass, it has no charge, and it travels at the speed of light, similar to X-ray. It has a short wavelength and a high energy, which means it has a high frequency. And it originates from the nucleus of a radioactive atom. Higher density materials are required to stop this type of ionizing radiation. So commonly a plate of lead is used to block the gamma rays. They are also considered low linear energy transfer forms of radiation. The higher the energy of the radiation also means that gamma rays possesses higher penetrating power. So yes, they can pass through skin and they can damage internal organs and bone marrow if they are not carefully controlled. So let's have a closer look at particulate radiation that come in the form of particles, alpha, beta, neutrons, and protons. These types of ionizing radiation is formed when the subatomic particles are ejected from atoms at very high speeds, and they possess enough kinetic energy to cause ionization, and this type of ionization is normally formed during radioactive decay. Particulate radiation originates from radioactive nuclei, which has enough energy to ionize matter. They are normally unstable, and in an attempt to regain its stability, the nucleus will emit particles of energy. It does so in the form of particulate radiation, of course, which includes those that I've mentioned before, alpha, beta, protons, and neutrons. The ones that you may encounter in practice are alpha and beta particles. So let's look at alpha more closely. It emits particles. We've already established that. It consists of 2 neutrons and 2 protons within its nucleus. These are the nucleons. It has a positive charge of +2, and it originates from the nucleus of a very heavy element, such as uranium or plutonium. Alpha particle emissions have a high mass, and they travel short distances in air. While heavy and damaging, they do not penetrate through the skin very easily, or not at all, should I say. They can be stopped by a piece of paper. So you could have an alpha particle in your shirt pocket, and it would have no effect or bearing on you externally. So that being said, although a small piece of paper can protect you from alpha particles, it is very damaging internally. It's an internal hazard. Like I said before, they are heavy, and they have a big mass and momentum. They are considered high linear energy transfer radiation and are released by the most deadly radioactive isotopes like plutonium and polonium and uranium and radium. Beta particulate radiation, similar to alpha, is emitted from the nucleus of the radioactive element, but it is 8,000 times lighter than alpha. It has a small mass and a negative charge and can easily be stopped by plastic or a thick layer of wood or aluminum. You can put it in an aluminum box and it will protect you from beta particles. Most radioactive isotopes do release some form of beta radiation. Like I said, they can be stopped by a thick piece of plastic, but if it does reach you, internal hazards are most prevalent. It can be damaging to the skin and the eyes as well if it's not controlled properly. And then lastly, let's have a look at neutron radiation. These uncharged particles are indirectly ionizing, so they have no charge and they are very penetrating and have enough speed to strike other atoms. So indirectly, they cause an impact and they give off a form of primary ionizing radiation, such as beta emission. The strength and the dose calculation factors will vary with this type of radiation. Neutrons are excellent at starting nuclear reactions because they are not repulsed by other charged particles and can cause certain radioactive materials to split. So they are quite often used for atomic bombs, for example. They are considered a medium linear energy transfer radiation because while they have no charge, they have a high mass. So let's do a quick comparison over here. Look at alpha. On the left, you can see the ionization ability is a lot more than it would be for beta radiation, and beta radiation has the ability to ionize a lot more than gamma would. Alpha, though, is the least penetrating of them all, and on the other side of the spectrum, gamma radiation is the most penetrating. So to review, alpha particles can be stopped by a piece of paper. Beta is a little bit more penetrating. It can be stopped by a thick piece of plastic or aluminum, or you can put it in a wood box or aluminum box. X-rays, they are very penetrating. They can pass through tissues 1 meter or more in thickness, and they are utilized by us to create images of the patient's body. Gamma radiation is very penetrating and can penetrate deeply into structures because it has no mass, no charge, and high speed, similar to X-rays. We don't use that as often in our field, although the radiotherapists that treat cancer, patients with cancer, they'll be using gamma radiation more. Either way, when they do use it, it has to be controlled. Neutrons is very penetrating. Why? Because it has no charge. It has a high kinetic energy when it is released. So I have included some videos for you to have a look at. I'll put that in D2L, and I will add links to these videos in an email to you. And before we wrap it up for today, I would like to discuss one more thing, and that's the discussion forum. So let's move on to that. So your first discussion forum topic will be posted in D2L today. It is worth 5% of your overall mark, and it is a think, pay, share activity. I want you to look at which types of nuclear radiation is the most dangerous. I want you to consider that and share that with your classmates. Other things that you will consider is this riddle. So look at this. You have 3 cookies. One emits alpha radiation, one emits beta radiation, and one emits gamma radiation. So you've got to eat one of them. You got to put one of them in your pocket, and the third one you have to put in an aluminum or lead box. Which one do you put where and why? Once again, I'd like you to think about this, answer this question for yourself, and then post it on the discussion forum and share that with your classmates. So there are 2 more questions for you to consider, also to be posted in the discussion forum. So I want you to assume for a moment that you are planning to move to Canada to live there, and you want to figure out the radiation you would potentially be exposed to if you were living there. And you can do that with using a calculator, an online calculator. The calculator includes information on how you can calculate your risk of exposure to cosmic rays from outer space. Of course, this will depend on the elevation and the latitude of the area you're living in. The dose calculation will include radiation from terrestrial radiation from the soil. It will include things like house construction. Do you live in a stone house? Do you live in a brick house? Do you live in a concrete house? It will consider things like, do you live close to a power plant? And how close? If you are living there, how close do you live to a power plant? It also considers what type of food you eat, so that you can calculate your dose from internal radiation. Do you eat a lot of bananas every day? Is there a possibility that you eat a lot of rice every day? Could there potentially be radiation in the food and the water that you are drinking? Another interesting one that you may not have considered before is people with porcelain crowns or false teeth. The material that is constructed out of can emit very low doses of radiation. So that will be included in your calculation as well. Now remember, in the first video we spoke about the banana factor and how you can use that to compare or understand radiation dose. So at the end of this little activity, when you're calculating your radiation dose, it will give you an answer in terms of, let's say the dose that was calculated is 1.2 millisievert. That's what you received per year on average. That is equivalent to about 18,000 bananas or 18 chest x-rays. So this activity is quite interesting. I want you to do it on your own. And whatever you discover, if you can share that with your group. And last but not least, the question you will be considering is number 3 on the slide. Would a 1 millisievert dose received over 1 year be the same as receiving it all at one time? I want you to consider, contemplate the answer to that question. Look at your textbook or online resources to find information and post the answer to that question online. Chat soon.